Okay, today we're going to look at tests for symmetry and even and odd functions. So symmetry is something you've talked about since elementary school. Specifically, these two types of symmetry with some of the language we're going to use with this probably started in geometry. Okay, but we have two types of symmetry that we're going to look at with our graphs. The first one is line symmetry. It can also be called reflection symmetry. Either way. So this says the graph can be reflected across a line so that the graph coincides with itself. Now, when you first talked about line symmetry in elementary school, you may have talked about it as folding the paper. Like if I fold it here, it folds on top of itself. But it's not really a folding, it's a reflecting. So this whole graph here, if I reflect it in the x-axis, it's going to just basically lay back down exactly where it was. All right, so there's your line symmetry. Then point symmetry. Up until geometry, line symmetry was the only type of symmetry you most likely knew about. But then there is rotational symmetry, and point symmetry is a type of rotational symmetry. I don't love the wording here, and I should have fixed it, but it says the graph looks unchanged when rotated 180 degrees about the origin. So it's not just a rotational symmetry. Point symmetry means it has rotational symmetry of 180 degrees. And our center of rotation is at the origin here, okay? So that means if I turn my paper upside down, which would be a rotation of 180 degrees, the graph should look exactly the same, okay? So when we talk about X and Y symmetry and origin symmetry, the x-axis and y-axis are common lines of symmetry. And then the origin is a common point of symmetry. Right? So we want to know, based on graphs and then also based on equations and based on tables, if our function or if our relation is going to have symmetry with the x-axis, y-axis, origin, or maybe none of the above. Right? So this says, and by the way, when I said functions and then, well, relations is what I really meant to say. We're going to look mostly at functions, but this is a relation, okay? This is not a function, but it is symmetric to the x-axis. So basically anything symmetric to the x-axis, not going to be a function. All right, so the following graphical and algebraic tests can be used to determine if the graph of a relation is symmetric to the x-axis, y-axis, and or origin, because it could be symmetric to more than one. Now, algebraically, when we're looking at ordered pairs and what happens to x and what happens to y when we reflect, that you started looking at least in 8th grade, maybe before that, but I know for sure it starts in 8th grade, where you think about which signs change when you reflect in one or the other. And if you get it mixed up, which a lot of times people do, you can just get it backwards. If you want to make sure that you know what's going on, you just pick yourself a random point. I'm going to pick this point right here. Okay? So we're going to talk about x-axis first. If I reflect this point in the x-axis, it ends up down here. So then I look at what changed. Well, my x value did not change. I have the same x value. So for every point xy on the graph, the point, well, x stays the same. And then y changed, but I mean, it wasn't a drastic change. All that happened was that we changed the sign. So this becomes x negative y. Okay, so for every point xy, x negative y is also on the graph. That would make it reflect a reflection in the x-axis, just like here. This would be x, y, this is x negative y, x, y, x negative y, and so forth and so on. Right? So the algebraic test, like if I have not a graph that I can look at, but if I have a function, then I could, if I have the equation, then I'm going to replace y with negative y, and then I clean it up, and I should get equivalent equations. So the y-axis, I'm going to take this same point, and this time I'm going to reflect it in the y-axis. So when I reflect it in the y-axis, it ends up over here. Well, this time, my y value stayed the same, and I changed the sign in x. Okay, so if I have x-axis symmetry, it's x negative y. If I have y-axis symmetry, it's negative x, y. So that means my algebraic test will be replacing x with negative x, and then resulting in equivalent equations. Now, origin symmetry, here's our rotation. Okay, so here's something you need to know about reflections and rotations, which, again, you should know from geometry. If you reflect twice and intersecting lines, or my intersecting lines, then it's a rotation of however many degrees this is times 2. Well, these are my axes. This has to be 90 degrees. So if I take this point, I reflect it in 90, and I reflect it again, that's the same as a rotation of 180 degrees. So that means that if I take this and I reflect it in the y-axis, that means I change the sign on x, and then I reflect it in the x-axis, I change the sign on y. So when you have origin symmetry, the signs change on both, and that results in a rotation of 180 degrees. So in order to test this algebraically, we're going to replace x with negative x, and y with negative y, and it should result in equivalent equations. Okay? So we are going to predict based on the graph, and then we are going to confirm your answer algebraically. It means you already know what the answer is when you're confirming it or justifying it. You're basically just showing why that's true. So when we look at this graph in number 1, it looks to be symmetric to the y-axis, okay? Not symmetric to the origin, because if I rotate 180, that ain't gonna work. If I reflect in the x-axis, it's not gonna look the same. But I do feel like if I reflect it in the y-axis, it's going to be the same. So then I have to confirm my answer algebraically. So remember, it says, if I have y-axis symmetry, I'm gonna replace x with negative x and show that I get equivalent equations. So for negative x, or for x, this is going to give me y equals, I'm using this right here, this is negative x to the 4th minus 4x, I'm supposed to be substituting here, 4 times negative x squared. Little side note here. I want to remind you that negative x to the 4th is not the same as negative x to the 4th. Those mean two totally different things. This means I take x to the 4th and then my answer is negative. This means I take the negative x to the 4th. This is actually going to give me a positive x to the 4th. So that means here I get y equals, this is going to give me x to the 4th minus 4 times x squared. Then I look at these two. This is equivalent to this. And so there is my proof. Okay. So let's look at number 2. So if I reflect it in the x-axis, not going to look the same. Y-axis, not going to look the same. But if I rotate it 180 degrees, and if you need to, well, if you don't have a piece of paper, then you turn your tablet upside down or stand on your head, I don't know. But if I rotate this to this, it's going to look the same, so I believe it has origin symmetry. So in order to test the origin symmetry, I replace both. That means that I'm going to get negative x times negative y equals 6. Well, negative x times negative y is x times y. That equals 6. This matches this, and I'm good. Okay? You have to show the substitution part of this. You can't just say, oh yeah, it's going to equal it because I can tell because it looks the same or whatever. You have to actually show that, your substitution, and then there's really no work. I mean, that's all that has to be there. Okay, let's look at number 3. So if I reflect this in the y, or let's see, it starts with the x-axis. So I feel like if I reflect this in the x-axis, I think it's going to look the same. If I reflect it in the y-axis, it'll end up over here, so no. Origin will rotate it over here, so no. So I'm going with x-axis. To test the x-axis symmetry, I substitute in negative y for y. So this is going to give me 4 times x plus 3 squared plus negative y squared equals 16. And if you don't have enough room, like if you're using Cami and the box is not big enough, you can expand it just like you would on your phone to make something bigger. Just the pinch and the zoom, you can make the box bigger, you can write in it, and then when you make it smaller, it'll look great. So then this is going to give me 4x times x plus 3 squared plus y squared equals 16. These two match, so I'm good. Okay, so let's look at number 4. So if I reflect this in the x-axis, I feel like that's going to work. When I reflect it in the y-axis, that's also going to work. If I rotate it 180 degrees, that's also going to work. So I think it has all 3 types of symmetry, which means I have to show that all 3 types work. So I'll start with the x-axis. So to test x-axis, I substitute in a negative y. So negative y squared minus x squared equals 1. Gives me y squared minus x squared equals 1. So that one works, right? And then I know some of you are already thinking, well, I can tell that the other ones are going to work. That's fantastic. However, it says to confirm it algebraically, so you have to write it down. So to confirm the y, I substitute in a negative x. So this is going to be, oops, it's going to be y squared minus negative x squared equals 1. So I get that y squared minus x squared equals 1. And that matches as well. Then I'm just going to write on top of my graph because I don't have enough room either. And for the origin symmetry, I replace them both. So this is going to be negative y squared minus negative x squared equals 1, which gives me y squared minus x squared equals 1. And I've shown that why all three work. Okay, so why don't you pause and try 5 and 6 and then come back and see if you agree with me. All right, so I'm going to look at number 5, x-axis. So I reflected in the x-axis, it's not going to be the same, okay, because it would look like this. That would not be okay. Y-axis, this part would be over here, so that's not okay. Origin, that's not going to work either. Now, if I translated this to the left one and this point was at the origin, then it would have origin symmetry. But so there is rotational symmetry here, but it's not about the origin. So none of those work. So my answer is none. And then I don't have to show anything. So look at number 6. Okay, so if I reflect it in the y-axis, I feel like that's going to be good. X-axis, no. Origin, no, because it would put it up here. So I'm going with y-axis, so I'm going to substitute in for a negative x. So y equals negative absolute value of negative x minus 2. So the absolute value of negative x is x, so y equals negative absolute value of x minus 2. That matches this, so we're good. Okay, so that's you justifying and showing it algebraically. Now, let's talk about why we really talk about this symmetry, is to talk about even and odd functions. Okay, so in this case, these are functions. Like before those, some of those were relations, not all of them were functions, but we're going to look mostly at functions. Okay, so a function is even if it is symmetric with respect to the y-axis. Okay. And a function is odd if it is symmetric with respect to the origin. Okay, odd is origin. The two O's go together. Even is the y-axis. You can think about y equals x squared. That's symmetric with the y-axis. Okay, so your algebraic check is that when we substitute, so this is a little bit different than proving if it's x-axis, y-axis, or origin symmetry up there. You are going to substitute in a negative x. Okay, so if f of negative x equals f of x, okay, so if I substitute in a negative x, then I should get f of x back. For origin symmetry, if I substitute in a negative x, then that should give me negative f of x. So in this case, I'm not substituting an x or a y or both. We're only using x for even and odd functions. And we either get f of x back, that makes it an even function, negative f of x back, that makes it an odd, or if we don't get either one of those, then it's neither. All right, so let's look at how this is going to work. So this says determine algebraically if the function is even, odd, or neither. That means we're not graphing it to look at it. We have to understand what to do. And then it says if it's even or odd, describe the symmetry. So there's some words that we have to use with this. So I'm going to take f of negative x. So f of negative x. That means I substitute in a negative x everywhere there's an x. This gives me negative x cubed minus a negative x. Okay. So then this equals, so negative x cubed is negative x cubed, and then minus a negative x is going to be plus x. Okay, so that doesn't look like this function here. However, so if it doesn't look exactly like it, I'm going to try factoring out a negative 1. So when I factor out a negative 1, that leaves me with x cubed minus x. Since this part does look the same, and I just have this negative 1 out here, that means that this equals negative f of x. So since it equals negative f of x, that means that this is odd. And then we write, because it says describe the symmetry. we say that it is symmetric. We can abbreviate a little bit. Symmetric with respect to, and since it's odd, it's with respect to the origin. Okay, so everything I have, pretty much that whole thing is your answer, because you have to show this part, and then you have to answer, and you have to give the words. So there's really nothing there that you can leave out. Okay, so let's try number 8. Again, I'm doing f of negative x. That's equal to negative x squared plus 6. So then this is equal to negative x squared is just x squared. So this is negative x squared and then plus 6. These two pieces here are identical, which means this equals f of x. Need to have that on there to finish that off. That means that this is even. Then I say it is symmetric with respect to, and since it's even, it is the y-axis. So it'll just be y-axis or origin. All right, so let's look at number 9. I'm going to do f of negative x. That's equal to negative x cubed minus negative x squared minus 2 times negative x. So then that will give me, that is negative x cubed. Then this will be a positive x squared, so minus x squared plus 2x. Okay, so since this does not match this exactly, I factor out a negative 1. So this is equal to negative 1 times, that would give me positive x cubed plus x squared minus 2x. Then I look at this again. This still doesn't match that. Okay, because if it did, then this would be negative f of x, but it doesn't. So that means it doesn't equal either one, and this answer is neither. It's not even or odd. Okay, why don't you pause and do 10, then look at it, then pause and do 11, then pause and do 12. Let's look at 10. F of negative x. This is equal to the square root of negative x squared minus 4. It's going to give me the square root of x squared minus 4. These two pieces are identical, so this is equal to f of x. Since I got f of x back out, that means that it is even, and I say it is symmetric with respect to the y-axis. All right, number 11. F of negative x. This gives me negative 8 over negative x, which is equal to 8 over x. So these are not identical. However, if I factor out a negative 1, that will give me negative 8 over x, and so that does equal negative f of x. So then that means that it is odd, and it is symmetric with respect to the origin. Then last one. Oh no, I'm sorry, we got some tables down there. But f of negative x is equal to the absolute value of negative x plus 1. And so this is not the same as this. So I factor out a negative 1. And then this part I can pull out of the absolute value, so that's the same as the absolute value of x minus 1. And this doesn't match either, so this one is neither. Okay. Now let's look at what we do for the tables. For the tables, same idea, right? Is that if does f of x, does f of negative x equal, does f of negative x, so f of negative x, if that equals f of x, then that is even. If f of negative x equals negative f of x, then that is odd. Okay, so those are the things that I'm looking for. So I'll look over here. So if here's f of x, this is my f of x, right? So f of x gives me this. F of negative x, which would be a positive 4, I get the opposite. F of negative 5, F of negative 5 and F of 5 give me the same number with different signs. F of negative 6 and F of 6, same number, different signs. That means when I take so if we look at this, this is 4. The F of negative 4 gives me a negative F of x. So I'm getting this right here. So I can say F of negative x equals negative F of x. So that is odd. So let's look at number 14. We can just use the positive to the negative if that makes it easier. F of 3 gives me 13, because this is my F of x. F of 3 gives me 13. F of negative 3 gives me negative 11. So if it would have given me 13 up here, so if this had been 13, it would be even. If it's negative 13, it would be odd. It's neither one of those, so this is neither.